Okay. So yeah, sign this barcode, please. Wait, am I?
You were a little bit loud.
I'm loud.
Just a little bit.
Well, that's
It's
fine.
It's fine.
Just they can lower the volume on their end in YouTube.
No. If you speak too loud, the gain, the whole microphone, the audio in itself will be too loud.
Well, guys, today's a little different. I'm gonna experiment. So I was gonna go over self-balancing binary search trees, but that's not really beginner. It's like advanced. And on that matter, so was quicksort, which some of my colleagues said maybe it wasn't, the best idea to go over that. But I digress. Today, instead of going over this very advanced data structure, I am going to do something different, and that is that we're going to actually have you guys solve the problem. So we're going to do LeetCode questions that are put out on the Discord server on interview training. So the question we want to go over today is, what's the name of the question? Lowest common ancestor?
Yeah, like a binary tree. Binary search tree or binary? No,
It
binary.
is binary search tree.
No, it's a binary tree, I think.
Binary tree or binary search tree?
Binary tree.
It's a binary tree.
Yeah.
So it's not binary search tree. Tree. Hello. Okay. All right. And the description is that you have two nodes. So actually, let me draw it out. What's the example they use? The actual. Let me just draw something out.
3516208.
3. That's not a 5.
Yeah, you might need to do that a little bit smaller.
Smaller? Really?
Yeah, it's a pretty big tree. Depth of 3.
Then I'll move it here. Depth of 3? Okay.
3, 5, 1, 6, 2, 0.
Like this, right?
No, 0, 8. You were doing it right. From left to right.
6, 2,
0,
0, 8.
Yes. 0 left child, 8 right child.
Oh, right. It's not binary
Yeah,
search tree.
It's a binary tree.
I keep getting into mine. This is not a binary
And then
search tree.
7, 4 for the 2. For the 2. Yeah.
Okay. So this is not a binary search tree. Y'all remember what a binary search tree? Middle, everything to the left is less than, everything to the right is greater than. It's not that. It's just a simple binary tree. And the question is that you are asked a question, right? You're given, say, two nodes, P and node Q, right? You're supposed to find node, was it T? Is node T? Is that how they describe it? Find T, where T is the lowest common ancestor of those two nodes. So let's say it's, this is P and this is Q.
Example is 5 and 1.
5 and 1?
Yeah.
Well, I'm going to do this one, all right? What's the lowest common ancestor of P and Q? Yeah, so then T would be here. Now let's say I moved, now here. What then? Which one is it? 3. That's the lowest one. That's the one they share in common. Okay? So you're tasked with come up with an algorithm that returns T. Okay? So that is the point of this problem. So, okay, how do we start this? You're returning one node.
So in the method we need like 2 nodes and a root?
No, so the nodes, these are the arguments. That's not a colon. These are the arguments, right? And then you return T. No. So yeah, you could have a case where Q is here. Let's say P is here. They don't have to be the same level. Still, you find a solution that should work regardless of them being in different levels. Okay, you. Yeah.
Can a lowest common ancestor be P or Q?
Yes, actually. So let's say it's like this. So what's the lowest common ancestor then? Q. So it's 1. So yes, P or Q can be the lowest common ancestor. Thank you for clarifying that, Lazaro. Okay, so then T would be here. All right. Okay, so any ideas?
I want to say something on that.
Yeah.
We first have to find where P and Q is, and then like pop the stack and to the
Okay.
top.
So a stack. So this is So how do you mean? Well, they do give you P and Q.
Oh, they give you the nodes.
They give you the nodes. They give you the nodes.
Right.
The nodes are there.
Start from the lowest common ancestor of the whole tree.
The lowest common, which is the root.
The root.
Okay. And then what do we do?
Go through the bottom of the tree until we find P
Or Q?
or Q.
Okay. So where is it? So how do we start it off? So I'm gonna erase this part right here. So we see that. I don't know. Just solver. And it's P, Q. No, let's say Q. Sorry, guys. Okay. So root. Okay. So oh yeah, that's right. Yeah, so root is in here. You're right. Okay. And so what do we do? This will take in the root of the tree itself.
While the root is not P or Q.
While the root is not.
Over run to the left or
Oh, okay. So what is P? Do you think P is going to be on the left or the right?
The left.
It could be on any side.
Oh.
Yeah, it doesn't matter. So root has to be either P or Q, right? So we have to check for that. Actually, do you have it with you? Right.
What are you talking about?
Yeah, it's that part right there. So we're going to need a helper function, but on top of that, we need a global variable. Well, global in the scope of this function. So we have the class solution. This is a function in the class, and self refers to a variable that can be accessed in any part of the class, right? So say you make an object that has an answer, right? And we'll say it's null, it's none. And then we have a helper function, and this is the recursive one. Okay? And of course, this is going to be recursive, right? We have to say, put the condition that the node is valid, it's a valid object, or else, do something else. Okay, so let's say we're at a valid node. Like, what do we check for? Okay. So we have to say we have a current value, right? And it's at node, right? It's equal to P or I'm running out of space.
Yeah, I know.
I'm running out of space.
It's erase the tree.
Huh?
Erase the tree, I'll write it here.
Okay, yeah, can you write the tree over there? So I'm gonna wait, let Lazaro write this tree.
Oh no, I have it here. You can continue.
Okay. Oh, you have it there. Okay. Just keep memory of the data structure. Okay. So we have a Boolean, and we make sure, hey, is it P or Q, right? And it could be one of them, or it could be none of them, right? So that's going to be held here. Okay. Then what? So we check the condition for, say, the root, or maybe any that isn't P or Q, right? And that, so the current node we're at could be it. It could be it. But first we need to find the other values. And what do we need to do? We need to recursively traverse where? Through the tree. In which directions? Yeah. So this is gonna, okay, so this is going to be a function that returns a Boolean. But see these self ands, what do you think we're gonna do with this?
You're gonna store the parents?
Yeah.
References?
We're going to, our answer is gonna be in here, and it's gonna be global. The scope is gonna be global, so say we're going recursively down through, helper, going we can still change this, right? It's, it's not gonna be in the scope of one helper call, it's gonna be in the scope of the solver, which holds the helper. So we get the left result by, recursively calling helper on node.left. And the same thing goes for right. Okay. Makes sense so far. So we're trying to find it. And it could be that ands is actually going to be found here or here. Because maybe it's not the root. Maybe it's actually a child of the root or a child of that child. Does that make sense? Right? Because, did you put it again? Yeah, because let's say P and Q are 7, right? So T is going to be 2. So that means that we may actually end up having to go left and then recursively call again and go right. And that's where we store self.ands. So we're going to change self.ands at some point. And when do you think that is? When do we change self.ands to get the actual lowest common ancestor?
Let me do that part.
Yeah. Okay. Actually, yeah. Again? Yeah.
Remember the possibilities that we talked about? Either the left or right subtree, or the current node is P or Q, and then the other node is not left or right.
Yeah.
I kind of just said it.
You kind of did just say it.
Python is so and and ors.
I have a lot of and and ors here. All right.
Wait, give me the marker. I'm doing this.
You're gonna write something. Okay.
Say this was P, right? This was Q. Does not look like Q. And so far what we've written,
Yeah.
what is curve set equal to?
Yeah.
So
In that part.
if we find Q or P and we haven't found the other one, I know that that one is the lowest common ancestor.
Yeah. But you want to make sure, you need to, I don't want to give it away. So if you know curve is equal to true here, by that, because if node is equal, let's say this is node, we're turning it right here. Node is equal to P or Q. cur is going to be true right now, because that's valid. What do you have to do with the left and right? What do you have to check?
Those are equal to P.
Not exactly. Not that it's equal to P, because
We should show what you're doing.
yeah,
too.
kind of right.
Can
What if that was P? We can't directly look at left or right.
Oh, yeah. That's why you have to.
he's doing something with the board over there. Also, they can't hear what you're saying.
What is she?
Yeah.
He doesn't wanna hear me.
Oh, what? Oh, wow. Let me actually see what it looks like. Yeah, they can see it.
If you know this is Q, you're going to recursively call the left subtree and the right subtree, correct? And you know that if P is either in the left or right, it's going to return what?
Q.
It's going to return true.
True.
Oh.
Yeah.
I mean,
So-
the ancestor is key, right?
Huh?
If P is in the left or right subtree, the ancestor is key.
Yeah.
Yeah.
But you're going to recursively call the left subtree and then recursively call the right subtree. And if you're currently on either P and Q and your left or right returns true, that means that the other node is either in the left or right, and you can use return 5.
Yeah.
Did that part make sense? Because you know you found one node. This could either be Q, could also be P. You know you found one. Check if the other is in your left or right subtree.
Yeah.
If it is, then just return 5.
Actually,
So with left or right? Return true.
so yeah, it's kind of like that. But
But there's
it's
one
left
more
or, yeah,
check.
there's one more check with left or right, right?
You want to check the cur is true as
Yeah.
well.
So it has to be current and either left or right.
Yeah.
Because current could be either P or Q. Then you check if you've already found, what is it? Q, let's say you found P, where your cur. You need to make sure you already found Q,
Yeah.
right? So that's the check, which could be either in the left or the right.
So what logic does that boil down to? If you were doing an if statement, let's say you have your cur, your left, and your right. What type of check would you make?
So I'll actually get it started.
If here and left or right.
Yeah.
Perfect.
So that's the first check you do. If cur and another parentheses left. Okay. And there's another check.
How about now when they're split up?
Yeah.
One is in the
Oh,
left,
bring it.
the other is in the
Bring
right.
it. Bring it over. Bring it over here. Yeah. Let's say you're here,
Yeah.
but you did find it. You found it in these.
Yeah, okay.
Mm-hmm. So now cur is going to be false because neither P nor Q. But you found Q on this side and P on this side. So what's the check?
Left hand.
Yes,
Left and right.
exactly. So the other check is that you check if it's left and right. Those are the two cases you check, and it's in this instance where you change it. Oh, it's not correct. You set it equal to the current node you're on. And once you find the answer, right? Say you're here, you return false. Why do we return false?
So it doesn't keep.
Yeah.
the-
So we don't pick this, right? Because if we did, if this returns true, then, well, actually, it probably wouldn't happen.
Yeah, it doesn't really matter.
Doesn't really matter. But we just want to make sure this doesn't return as a valid answer because we want the lowest one, which is this one. So return false. Now let's say all of this failed, like, I don't know, we're here. Actually, that's not really the point. Let's say we're here. Yeah? Yeah, let's just say we're there, right? What do we return? Yeah. Let me just, I want to see if they can see it. Ta-da. Yeah, let's say you're there. So that means that if statement didn't happen. So that means we haven't found P in this instance. So cur is actually going to be true in this case. Why is cur true?
Wait, for 6 cur is true?
Yeah.
When you're looking at 6?
Yeah.
Really?
Or is it? No, it's
Oh.
false. You're right. It is
Okay.
false. It's neither. I'm sorry, guys. Okay, cur is false. But we do recursively call left, and left was true, right? Yeah.
The question you're going to ask yourself, what information do we want to pass up?
Yeah. For the parent, recursive call.
One has true.
Well,
Because
yeah.
there's children that is
But there also may not be. So we want to pass down we want to pass up the information of what was the result of the left, or maybe the right, or the current one we're on right now. Okay.
See, that part makes sense? We want to let the parent know, hey, I've seen either P or Q in this subtree.
Yeah. Also, the mere fact that the current one might have P or Q, or may not. So, let me see. This is,
You just missed the else.
yeah. Okay, so let's say the node was not valid. Well, so you return false, right? Because you didn't find the node, you just reached the end of the tree. False. If you're not at a valid node. Now, after we define our helper recursive function, what's the call that we make to this function? What do we call helper on? Yeah, exactly. So you call helper on the root. Also, this is a continuation of this solver. All right, we've escaped helper. We call helper on root. Okay, and then we do all the work, and self.ands is the one that's changed, right? And self.ands could be none. It could be the root itself. So then what do we return? Just, yeah, return self dot ands. And it's important that we have the self here in Python, because that indicates that it's a class variable, right? It's a variable of the class, particularly of an object of the class, right? Like this. Yeah.
So it's wrapped around the class.
Yeah, and this is in the scope of the class, and every variable here that's not self.ands is in the scope of the call of this function. Okay. So yeah, this was it. This was the code for that. And so, do you wanna run
You
it
guys
there?
fully understand it?
Any questions about what we just did?
I don't understand the left and right part of that if statement.
This one right here?
The second condition. No, the
So
or.
this one?
Yeah.
Okay, so let's say the current one was neither the P or Q. So, well, this fails. Now, but perhaps, maybe, in the left and right, we found P and Q. So that's this part. So that means that we found our candidate. That node, that current node, is as we see it now, it is the lowest common ancestor of P and Q. So that's, in this case,
Yeah, I want to do like a little diagram.
you want to do a diagram?
Yeah, or at least like arrows.
Oh.
So you can finish.
Okay, so in this case, P and Q were here, and left was going to give it true, right's going to give it true, right? So left and right are both true. So that means that this one is the lowest common ancestor of P and Q.
Yeah, okay.
Yeah, so that's the idea, and then we change ands to be this current node that we're on right now. Okay? And we return false because we don't want to pass up any information to this one. Because we don't want this to override what we found, because this will be higher.
It won't.
I mean, it won't. The way we've set it up,
The
it kind of...
right subtree will be false. So we don't need the return false. I just did that so I can like exit early.
Yeah, okay, yeah.
Okay, so
You return whatever, like just return.
Yeah,
you can do a return, you can not
he
do a
did...
return, it doesn't really matter.
This is code. He did it so we can exit early.
Yeah, just so like don't continue, even though the next.
Just to save time.
So what you said for this queue, right? The reason I said you want to think of it as the information that's being passed up. When you're here, you know your current is going to be set equal to true, because this node itself is Q. So you're going to return true to 6. 6 doesn't have a right subtree, so that part is going to be false.
Yeah.
But left or right, true or false, it's going to return true.
Or cur.
Or correct, yeah. Is going to return true to 5.
Yeah.
This 2, this 7, left and right, false and false. Current, false. Is going to return false to 2. 4 is going to return false. But now current is equal to 2, which is P.
Yeah.
So that
Cur is true.
so it now is going to be true or false or false. So 2 is going to return true to 5.
Yeah.
Once we're at 5, if we know the left subtree is true, we know
And-
that P or Q is on the left side. And if we know that the right subtree is true, we know that the other node is on the right side.
Yeah. So that's that second check in the
Yeah.
statement.
So
where
with,
we or.
with this, if left and right is true, we know that this is the lowest common ancestor.
Mm-hmm. Yeah. And so, but there's also the case where, and this is the first one, the one before that one, where we're here, right? And well, we're gonna return false on all of these. But what was cur here? True, because cur is P. So it's gonna be cur, which is true, and either left or right. What was right? But it's oring with left, which was true. So that's that other case. And so because of that, then we override self-ans to be this. And this is the lowest common ancestor of P and Q, which just so happens to be P itself. Okay? So that's the explanation for that part. All right. So I think, this covers this question. What else do you think we should talk about? The trick. Oh, there's a neat little trick Lazaro just gave out. Do you want to do it here?
I'll do it there.
You do it there? Okay, so I'm going to erase everything. Is that fine?
Actually, I'll do it here. I'm kidding. I can do it in a good place.
Just pick a place to do it, por favor.
Yeah, I'll do it there. I'll do it here. Don't erase the code. I'm kidding.
See this? What I put up with, guys? Whatever. I mean, maybe I'll leave it like that. I'll leave it like that for now.
No, I'm not gonna write code.
You're just going to show them the trick.
Yeah. Leave it.
Or maybe we can make them write the code for that trick.
Oh, yeah, sure.
Yeah, you guys going to write it. You're going to come to the board.
I'll do the same tree. Are you my boom arm guy?
Yeah, I am. No, but the boom is overhead. It's like this.
You saw the dog?
Yeah, I saw the dog.
Okay. So let's say this is your tree. There's actually a pretty cool trick on how to solve this question pretty easily. Every single time you visit a node, oh, I'm sorry.
Yeah.
Okay. Every time you visit a node, you want to mark it with a value. So this 3, I'm going to mark it as 1. And then I go to the left side. This 5, I'm going to mark it as 2. This 6, 3. Then I go back to 5. I have already marked it, so I don't want to overwrite it. Now we have 4, 5, 6, 7, 8, and 9. Yes? It's what? Oh, okay. So you guys see how I filled in the rest, right? Or do you want to explain it? So I see this one first, 1, then 2, 3. I go back to 5. I don't overwrite it. I go over here, 4, 5, 6. Then I go all the way to right, 7, 8, 9. If you write out this sequence, so I'm going to write out 1, 2, 3. Then I go back to 2, 4, 5, 4, 6.
I think you may need more space.
You think so? Oh yeah, this will be pretty long actually.
Yeah. We'll just
4, 2, 1, 7, 8, 7, then 9. I mean,
Yeah, no, I think you will just write out the last. I think it's
Okay.
2.
7, 1.
Yeah, okay. I was afraid.
So how did I get this sequence? I started at the root, 1, then 2, 3, back to 2, 4, 5, back to 4, 6, then 4, then 2, then 1, 7, 8, 7, 9, 7, 1.
So let's, you wanna set P and Q for
Yeah.
the sake of this. So just,
Okay, cool. Yeah, let's just make sure it's going to work. Let's say now your P is 2 and your Q is a 0, right? What's the lowest common ancestor of this?
Yeah.
What?
You said 3.
Oh, 3? Yeah. So another way you can do is you can go up to the first time you saw 4 and the first time you saw 8. And then within that range, the smallest number is your answer. So the one that's assigned to 1 is 3. Huh?
Makes sense, right?
Yeah. So if we can also do it like, say Q was 5. First time you saw 2.
Could it be the last time you saw it? Last time you saw 4 maybe?
Why would he do that? Is that would be like increase your string?
So it decreases.
No, like increases the size of the string you have to go through.
No.
So the first time is only all you really need.
But then you come here,
But there's no need to check these.
but then you'll be less. You have to, because you're doing a linear check on this
Yeah,
side,
and then 2 and 4.
and it'll be smaller.
No, 2 and 4 is this side.
Okay, what I'm saying is that you say the first 4, but about the last 4, that will make it closer to the first 8. So it will be a smaller check to see what smaller.
Why 4 and 8? Where are you getting the 4 and 8 from?
It's 4.
It's 2 and 4.
Oh, you changed it.
Yeah.
You changed it.
Okay.
I didn't notice that.
Okay, so the first 2 is here. The first 4 is there. And then the smallest number within the range, of course, is a 2. And that's your lowest
Okay,
common
no,
ancestor.
That's my point. You could just go to here and you just compare the smallest one of these 2.
Okay, yeah, no.
You
I
can
don't.
do that.
I don't think that'll always work because your last 2 is this one
No, I'm saying the last 2
before your 4.
This 4, yeah.
So your first, second one, and then your
Yeah.
last other one.
Yeah.
I feel like that might be buggy.
No.
Would it work?
What do you guys think? Do you think just picking this 2 instead of this 2 because it's closer for a linear check on which is the smallest one in this range of values?
Yeah, no, that makes sense. That makes sense. Yeah, okay.
I don't know. It's like a debate.
Yeah, but now that depends on which one. That says that's saying the Q will always be first and P or something.
Well, the Q-
What if it's backwards?
In this case, then it's the P. Just return this. Okay, so it's a hash table.
I love
remember?
discussing things.
This is a hash table
Uh-huh.
of. So the key is the node, and then the value is the number, and we have the list of numbers. Or is it the other way around? Actually, not sure.
Let's not confuse them.
Okay.
The key will be the node. The value will be the sequence, the time step
So
we
we
saw
get the
them.
value for the smallest. We get the smallest key,
Mm.
right? And that key could be either P or Q or neither,
Mm.
right? And it corresponds to this node. This is the same node as this node because it's the same number, right, guys?
Yeah.
So it choose this or this? It doesn't matter,
Mhm.
right? It's gonna be the same node. So you just return the node of that value in that hash.
So you're
table
saying
set.
choose the smallest of the two or the four?
Yeah, 2 or the 4. In this case, if
Okay.
we just decrease.
Yeah,
the
that might
range.
work.
Yeah.
That might work.
Yeah.
Okay, cool.
Yeah.
Okay, anyways, you guys see how it worked out?
Yes.
Pretty cool, right?
Yeah.
Yeah. What's the bad side about this?
You could need a very big, right?
Yeah.
Yeah.
Your space complexity will be O of n.
Yeah.
The other one was
2 is O2n.
yeah, still O of
So
n.
Well, yeah, I know. But you need an array
Yeah.
for the traversal, and you need the hash table on the other side.
So it's still O of n, but
Yeah. The other one you
Yeah.
just return and that's it.
the other one's O of 1, and then O of n time complexity. This is still
You mean
O of
space,
n
you
time
mean-
complexity.
You mean space?
The other one.
O of 1 space.
Yeah, I said O of 1 and then O of n time.
O of n time. Yeah.
Yeah.
Okay. Yeah. This is O of n space and time. So the other one is more efficient.
Anyone? You want to try to program this?
Oh yeah, write the code for this guy. Carlos, Paulina.
Carlos? The floor?
The floor is gonna do it.
No? Come on. Okay, at least let's talk it out.
Yeah. So we know what we need to set up, right? We need to set up the two.
Got a number.
Am I gonna? Should I write it somewhere else? To keep it here?
What? Oh, you are the code there since I started.
Yeah. So I'm gonna write the code here now. Hopefully, I have enough line. Alright. Yeah, that's a good color. So, I guess I'll put solve again. Solve. Alright. And so, let me think about something. Yeah, I'm running out. Hmm?
What?
What happened?
I can't see you.
No.
Oh no, you have to bring it here.
I have to bring it here. Alright. So first we have to do and then I guess, what do you guys want to call that array we did? Traverse? Travel. Oh, I just call it travel. That's going to be a list of how we traveled the nodes. Okay. So I'm thinking Mess up that H. Actually thinking, how do we keep track of
The what?
the biggest number? Okay, I guess we need another value, right?
What are you saying?
Okay, so I'm 1, 2, 3, right? So it's gonna be 1, I set that up in the table. 2, I set that up in the table. And 3.
Oh, you're talking
Then
about
I'm
counter.
I'm
Yeah, you
trying
need a
to
counter.
I need a counter.
Yeah.
Can I do it? Can I just have a global counter?
Yeah.
Okay.
I think that's easy.
I think I'm just gonna do a global counter, guys. And we're gonna set that equal to, we'll set it equal to 0 at first. And so we did the helper. In a node, right? So we do need, I think we do need the values, right? We're gonna need to store 2 other values for the number for P and the number for Q.
What?
We need to store where we find them so that when we're going through the
Oh.
list, right?
Yeah, sure.
So,
Yo, ask them.
okay, guys, what do you think? I'm having a little bit of a quandary writing this up. So do you guys know what I'm doing?
Like what I'm reading is, when you go to a child, you add to the counter, right?
Yeah.
When you go back, you subtract from the counter.
We're not gonna do that. The point is that we're doing in order. Well, we're doing,
Like, check the node.
actually we're doing like pre-order. We're doing pre-order, right?
Yeah, current node and left and then right.
Yeah. So, what we want to say when, put it back.
Well,
So this is 3, right?
yeah.
Then we go back up, but then we want to make the right 4. That has to be in relation to this 3. The same thing goes here, like 6, and then you have to go back up 3, and then that one's 7. So-
if you're calling it recursively and the left goes first, then it'll add up the left, and then we go to right, and it'll keep going from the counter that you already.
Right.
Right.
So, since it's left, when you go all the way to the right, it'll be 3. When you go back up to the right, then that would just keep adding to the counter, so it'll be 4, and then it go down.
Yeah, okay. That's a good point. So, but I also want to, I want to get, say, where are the values for P and Q? Like, is Q2, 3? So do you guys think we should have 2 extra values for P and Qs?
You should probably, if we see the QRP, just save the number that we had so far.
Yeah, you could probably just save it as you go along.
After the fact? I mean, after we do the recursive?
While you're
Well, I
recursively
mean,
doing it.
the thing is that this is going to, so the key is going to be the node. So if we pass in the node, and then that should give us the number.
Okay.
So,
So why are you keeping a counter then?
well, that's just to like give, set the values in the table, right? I'm supposed to increase it, like travel, in travel. Okay, so I think we have more or less, everything to help us. Node, right? So of course, self dot counter, when we call it, we're gonna increase it by 1, and self dot,
Okay, I don't think they can see about that.
they can't see it? Oh, sorry. Let me put it back here. So yeah, so this is just part of the code. So self table. So we said the node was the key, and the value is going to be the current value for the counter, right? Right. Okay. And so what do we do then? Well, then we have to go to the left and right and do that. So helper right. All good so far, right? You don't think any problems are going to be made? We're confident about this?
So note if it's not, you have to even if.
Okay, yeah, good point. So, yeah, if node, yeah, it's kind of small, but we're supposed to check if it's a valid node. If not, then stop recursively calling it, because that would give us an infinite loop. Recursive stack would be too deep, which would be the technical thing. All right, so then, you gotta what?
We have to add the numbers to the array.
Right. So, actually, it should have been before. Let me erase this. So, yeah, the first time we see it, we put it there. And the last time we see it, we also have to put it there. So, now that I think about it,
Yeah.
you have to put it twice. So we actually, the middle number should have been there twice, no?
Huh?
Like the middle number should have been there twice.
What are you talking about?
Like when you reached a leaf,
Oh.
the leaf should actually be there twice in the list.
Should it?
Kinda should. Like look,
Oh,
see?
yeah,
It would have to, right? Because then I would have to put it in there. See, what is it?
Check and then we just go back.
Self.travel.append. Right? I have to append what exactly?
The counter, isn't the counter the key of the creator?
Well, yes, but that's the thing. We wanted to stay this what it was before, right? I mean, yeah, we could just put counter, but see, that's the thing. We might put the wrong value if we just put counter. If we set it to 5, but we're back at node 1.
Yeah.
So we don't want to do that. Confusing?
I was thinking of taking the key. I don't know.
Well, the key is going to be the node, right? And it's going to be what counter was the first time we saw that node. So that's what we want to put in the travel, right? The address, right? The point, right, at which we saw it. So this would be actually self.table.
What if we ignore all the nodes until we find P or Q?
See, that's the thing. We're not going to do that. The only point here is that we want to get the list of the numbers, right? Remember? We want to get the list of the numbers we traverse. And that number is going to correspond to a node, right? So, yeah, we're actually going to do that soon. We're going to do that after we do the whole recursive stuff. Okay, so let's say we added the first time. We added the second time after what? What do we have to do? I erased it.
Which, well, okay.
Yeah.
We'll have to check that if it's
left,
P or Q.
Yeah, left. So, no, not yet, not yet. We're actually going to do that after the recursive stuff. So, I added it to the travel, right? And now I have to call helper again on the left and the right. So that was left. That's right. Right. And then after I do it, I have to do it again. Because I need to say, hey, I went back to this node. I misspelled travel in the upper one. Ignore that. Okay? So then I finish with the helper. and I call it on root. So after I call helper on root, I set up all the values for the table. Every node has a number and how they were, viewed. So what do we do now? What do we need to find? P and Q. So we say P val equals right, and we just pass in P. And then Q val equals right, because those are nodes, and those are the keys. Okay, so now we need to go through the travel table. Is there anything we need to do before we check the travel table? What do we need to do? What do we need to do?
You just slice the rate in between those two.
Okay.
Those two fields.
Well, these are values in the array. These aren't indices. They're not indices. So then, what do you do then? Right?
Oh, search for P&Q.
Search for P and Q. Well, which one came first is my question. There's no way of knowing? Why not? What if we just keep a track of which one was found first? Right? So, less equals, no. So, and bigger? Yeah. If P val greater than Q val, then we change it. We say, let me see.
It's not ordered, right?
What do you mean?
So, for example, in that example, we have 9 and then 7.
Yeah, but we need to actually. Let me get it back. Let me open it back. All right. So it's semi-ordered. It's sort of ordered. The first instance of 2 appears before the first instance of 4. And in fact, 2 will appear before 4. 4 will always appear before 5. I mean, it will appear after, but 4 is appearing before 5 the first time. 5 is appearing before 6. 6 is appearing before 7. So it's sort of ordered. It's not really ordered. But that's a good thing, because now, so kind of like what Lazaro did. So we get the bigger one. Actually, I might change this code. Erase this back here. And can you see the bottom?
They can see up to the Q part.
Yeah. This is a little long. Okay, so if the less one, as in first, why don't I just call it first, right? And if the first one is actually greater than the second, then just swap them. All right, that makes sense? Just swap them. if we turns out we were wrong about which one came first. Okay. So then, yeah. So what do we do now? Now that we've decided, we know which one comes first, which could be either P or Q, which one comes second. We just work with the table, right? The travel table. So how do we go about that, right? And I'm gonna go with what you said about the first value of first.
So much easier.
Yeah, it's actually really so much easier if we just did that. So we do need to splice it, right? I mean, we don't really need to splice it. We could just say,
For the question itself, I don't think you can do P dot value or Q dot value.
p-val. No. This is just a
underscore? Oh, okay.
underscore. It's a variable. It's not a.
Okay.
No. And then like it would be in, the node is a key, like before. Okay, so we swap first and second. So what do, right? We find the first one for first, right? We find that index. Actually, we'll just do that. So first index equals -1. For, I guess, n in self.travel. If n equals, I guess it's gonna have to be first.
Use the index function.
Huh?
The index function.
What do you mean?
Like an array dot index of this value. And it
Yeah.
returns the first.
Yeah. So I find the first occurrence of the first number, and I
Yeah, that
store it.
sounds better.
And actually, I should do enumerate.
No, do what you said.
What do you mean?
Dot index.
Is that a thing?
Yeah, it works.
Hold on. How do you n.index? Is that how you do it?
Just self dot travel dot index, and then the number, the element.
Okay, but I'm going through the array of travel.
Yeah.
Yeah, and I'm doing for n in self.travel.
All you need is the index. Then you can get that subarray and return the minimum number. And then convert that minimum number to the node.
Okay, I know. Yeah, I know what you mean. Okay, I'm gonna do this. I'm confused. I'm just gonna do this. Okay. So I'm just gonna do in enumerate. Not travel. Okay. So goes I. Do we know what enumerate does? Okay. So basically, enumerate turns an array of the index and the value at that index. So I is the index. So I get the index, which I said it. So now before, how about this? Do a trick. Let's find min val equals it could be,
I think that's where you messed up.
where?
Because for me, I had two tables. I had this node to C and then C to node. Because there you're gonna get the minimum C counter, right? Your minimum C. You need to turn that C to the node. So you need two
What do you mean?
hash maps.
Why?
What are you doing?
Okay, look. So
No, this. Okay, this part is going to return whatever self.counter is, right?
well, this is
So your travel array
Yeah.
is going to have the C, the counter numbers.
This get
How
no.
can you convert that counter number to a node? You need two tables. A node to counter and then a counter to node.
Why?
Once you get your minimum value, what are you going to do with that? That's not a node. That's just the counter for that node. Are you going to do
You
another
can get-
helper function?
But you can get for a hash table, you can convert
Or
value to
you
key.
can look at the values?
Yeah, you can convert value to key.
I think it's cleaner having another table value.
Okay. I mean, yeah, you can convert. Yeah, I'm doing this.
You're going to do dot items and then look at the values?
Yeah, or something. I don't know. Okay, I'm gonna. I don't know what you just
Also,
said.
then I throw an error.
Why?
Because I did it and it didn't work.
Which part? Which part?
For me, I appended to the sequence after calling left and right. If I just do it before, how you have it, right?
Mm.
And then after. I'm also checking you have the left and right nodes. That's how I got rid of that problem you noticed. Or you pointed out. Here, I run this. It doesn't work.
Let me see. I'll put.
By the way, your code is long as hell.
It is long. How would you code this?
Like this.
Yeah, you're doing well. I mean, that's because you're doing this thing. I was actually writing it out.
No, we also have like for loops and stuff. What she said about indexing, that's way better.
Which one is it? Which one is it?
Look, you can just get the index of start and the end, and then do a subarray. Take the minimum between the.
Oh, that's what you meant. That's what you meant. Okay. Okay.
I'm sorry for pointing at you. I don't like pointing at people. I'm sorry.
I don't care.
Yeah, I know, but it's just a thing. I'm sorry.
How do you do it? How do you do it?
Yeah, I need to. It's her.
So is it first index, second index? Equals
self.travel.index. First.
dot index. And then
So enumerate returns like a list of tuples,
yeah.
the index and the volume.
Yeah. That's why in the for loop you see two variables, because it's unpacking that tuple.
Oh, you like
Yeah.
Okay. And then min val is equal to
The minimum in that subarray.
min in
Self.travel.
yeah.
And then slice. But inclusive, so +1 for the second index.
It doesn't matter.
It does matter. What if it's at the end? Just be safe and do +1.
Okay. Actually, you're right. It does matter. He matters.
You gave my life back to the next.
So the +1 that I'm doing here means is inclusive. Okay. So we get the min val, which is the minimum number in the middle, right? The minimum value in the minimum from first index to second index. Okay. So actually, this is first occurrence based, right? This index thing.
Yes.
Okay.
Exactly.
Okay. And so then convert that back into
Yeah.
the node key.
Oh, add your for loop.
I actually don't know this part. I don't know this part. How do you?
That items.
Values?
Oh, so it's table.items?
Yeah. And then you get the key and value pair. And then see if the value is equal to mid value.
Okay, so
If it is return key.
okay. For what is it? N in
No. K, comma B.
okay.
Bro, you've been doing too much Java, man.
It's been a while. No, I've only been doing Python. No, JavaScript actually. for key values in self-failure. So the items, right? If equals k hold on a minute. V. Return K. Okay, do you guys get that part? So the min val is the value and the key is the node. So return that key node, which is, the node which is going to be, oh, well, I have to, can you move it up?
Oh,
Move it up. Yeah. Which here in this instance is going to be splice of here to turn that value into the key, which is that node. And that's that part. Make sense? We good? Anybody confused about
What's there if min val?
equals that value? Yeah. So we're trying to find, so it's a number, right? 2. But that 2 is a value in this table that appears only once. It only appears there once. Although he did tell me there were some problems with this, compilation problems.
No, like it's just wrong.
Is this wrong?
Yeah, it compiles, but it gets wrong. Yeah.
Let me see. Is it an ever increasing list?
What do you mean?
Like, is counter actually not?
No, counter is being incremented. I think it's just like the sequence of steps.
So we might have been doing this wrong. Okay. Well, help me out a little bit.
Oh, okay.
Yeah, help me out a little bit. So which part? No, come here.
Yeah, but I did a completely different approach.
Why not just bring the camera? Here, just grab this.
Okay, let's try to see if we can find an issue, right?
Yeah, let's debug.
Yeah, it looks right. No, I'm kidding.
Wait, what?
Didn't you have the problem with the 2 appends? The helper?
Yeah, that's the thing. He has 2 appends, but I have 3.
You have 3 events.
Yeah. I do it after calling
Oh.
the left and the right.
Yo, okay.
That might be why, because that throws the sequence off.
Yeah. We do it again.
Okay.
And okay, maybe here and here.
Yeah.
Yeah. Okay, duplicate it. My mistake. I didn't notice that. So then, actually, right here, that 3, that should appear 3 times in that list.
For this maybe, but for me, I checked if there's a left. If there's a left node, it's not going to hit the leaves and it's not going to repeat itself. So I do if node dot left, then do this, and then add to the sequence again. If there isn't, there's no need to add it. Your array will just be longer, and you don't need that.
Recursive wise, this seems simpler, right?
Yeah.
I don't know. What do you like? What do you like more, this solution or the one we did before?
Yeah, for sure. Like, 100%. Like, this is dirty code.
Yeah, this is long and
Yeah,
not,
it's way too long,
not,
and-
not optimized.
Yeah, it's long for no reason. It's like
Yeah.
long to be wrong.
Long to be wrong, guys. But no, there's just, there's always more than one way to solve a problem. This is one way, and I didn't know this trick. He showed it to me.
It's really a trick if it's like a lot worse than the other version.
It's not that
What if
bad.
you don't know the other version
That's true.
during an interview, but you remember this trick?
You have 2 options.
Why?
Yeah,
Well, I mean,
don't
like,
do it.
'cause-
Because look how long that is.
I mean, this is long, but maybe conceptually it makes more sense intuitively. And if you forget the original one, hey, I can fall back on this.
Yeah.
Hey guys, I know how to solve this way. It's not as good, but I'm willing to learn. And you just tell them that, and that's it. So, yeah. So that was the solution. I don't think we have more time, right?
No, it's not a solution.
We're out of time, right?
Uh,
Yeah. Wow, we're just out of time.
yeah, we are.
We are. I wanted to go over one more, but I guess we're not gonna have that opportunity.
Isn't this still not a solution because it had like the error that you got?
No, that was no. It wasn't.
We can look at the one that actually like gets accepted by LeetCode.
Yeah, I want to take a picture of this. I'm gonna take a picture of this. Just I'm gonna
Just for
actually,
that.
I'm gonna submit this and see if
So,
this works.
I have a question. Like def solve, that's supposed to be inside a class, so you would need like help.
Yeah, yeah.
And then for the inner one, helper, do you need it?
No.
No?
No, yeah. Because that function is inside another function.
So you don't need this help,
Yeah, you don't need stuff, yeah.
only in the other one.
Yeah.
Yeah. Took a picture of that. I'm gonna probably submit this. See if this works. Our work, right? We did this. Okay. So yeah. So tomorrow, Gary's having a lecture on. Do you know what he's covering?
Mm-mm.
You don't know.
Mm-mm.
No one knows.
No one ever knows.
No one ever knows. But we will know what the Friday lecture is after tomorrow, which is gonna be just a review of that, right? 9:30 a.m. to 10:45 a.m. You won't be there? You? Well, that's fine. But the Friday review lecture is at 3:30. I also was thinking of doing something a little new, which is basically what we just did, but maybe in a more casual setting. Like maybe either this computer lab or maybe in PG6, and we just do whole lot of LeetCode problems that we've assigned, and you guys work on it, and you guys explain to each other why you arrived to the solutions you did. Just explain it to people, yourselves, because when you explain something, you learn, you really let it sink into your mind. So I'm thinking about it being bi-weekly. So bi-weekly we have the binary search nights, which is gonna be. Do you actually want to do a binary search night this week to make up for last week?
I'm in midterm.
This week is midterm?
No, for me.
Oh, for you.
Yeah.
So
Wait, if you want to do it, you can go ahead.
I don't know. I feel bad. I want you to go. I feel bad. So, who wants to do it this Friday? To go to do LeetCode problems.
At 3:30?
Maybe after, like maybe 6 to 8.
So I probably have to leave early, but
I mean, if you can't come, it's okay.
And I wanted to come to the big workshop, so I might as well go to whatever.
The Figma is at what time?
5, I think.
5? 5 to.
Yeah, so I might as well go to what's before or after.
So I think if Figma's at 5, then 6:30. 6:30 to 8. I'll probably just have, a room set up. Maybe I'll even use the same room. Yeah, I'll use the same room. We'll just do it there. What room is the Figma, Lazaro?
Dude, you don't know any of this.
1:15 maybe.
1:15?
You want to know? Go out the door and look straight down.
Like the same one with the Django work.
I'll do it for you.
Talk to me. Yeah, talk. Oh, okay. So Lazaro's gonna go
Yeah,
outside.
the post is right there.
The post is right there. It has the room. I don't know the room. I'm sorry.
Class at 5, so I'm not gonna go.
You have class at 5? That's all right. 6:30 to 8. So.
So it's gonna be here?
116.
I don't know. I'm what 116?
Yeah.
So I'm thinking about it. Is there gonna are they reserving the room? Do we know if other
Probably,
people? So maybe somewhere in PG6, like a classroom, like 114, 6:30 to 8, 8:30. So, yeah, around that time. So it's gonna be. You can come whenever you want to. It doesn't matter. It's just also gonna be social. So, it's not gonna be like me teaching. It's just you guys working on the solutions together. That's all it is. So, just look out for that, and look out for the Figma workshop too, which is 5 p.m. PG6 room 116, right? Okay.